Okay, we are now at section 4.5, Tangential and Radial Acceleration. So here we are. All right. Consider a more general motion as shown in the figure. You can see the radii of those two circles. Actually, there's three circles. It's only a partial on the at C. The radii of those three circles is very different, and the velocity um, is different. You can tell that from the tangential acceleration vector. At at A is forward. At at B is backward. That means it's slowing down, and then at C is speeding up again. You could almost think of this as like maybe uh, a ball bearing riding on a track. You know, it's going to slow down as it goes to B. They don't really describe what it is, but I'm just giving you something to conceptualize. Okay, let's consider a more general motion. The particle moves to the right along a curved path. The velocity changes both in direction and in magnitude. The velocity vector is always tangent to the path, and the acceleration vector A is at some angle to the path. Um, At each of the 3 points, A, B, and C, the dashed blue circles represent curvature of the actual path at each point. The radius of each circle is the path's radius of curvature at each point. As the particle moves along the curved path, the direction of total acceleration vector A changes from point to point. At any instant, this vector can be resolved into two components based on the origin at the center of the dashed circle corresponding to that instant. The radial component AR along the radius of the circle, and the tangential component AT perpendicular to the radius. So the total acceleration of a vector A is written as a vector sum of the components. So the acceleration is equal to the addition of the components A radial plus A tangential, the radial acceleration plus the tangential acceleration. Okay, the tangential acceleration component causes a change in speed v of the particle, the component parallel to the instantaneous velocity. Its magnitude is given by A tangential is equal to dv dt, just the what we're used to seeing. Okay, the radial acceleration component arises from the change in direction of velocity vector. So AR is equal to minus AC equal minus V squared R. Let's see so the radius R is the radius of the curvature of the path at the point in question, and the magnitude of the radial component of the acceleration is the centripetal acceleration. Even in situations in which the particle moves along a curved path with varying speed, we can still use centripetal acceleration equation because it gives the instantaneous centripetal acceleration at any time. The negative sign in the last equation indicates that the direction of the centripetal acceleration is toward the center of the circle representing the radius of curvature. The direction of it is opposite that of the radial unit vector r, which always points away from the origin at the center of the circle. Because the radial acceleration and the tangential acceleration are perpendicular, the component vectors of A are shown, the magnitude of A is shown as here. The magnitude, A equals the square root of the radial acceleration squared plus the tangential acceleration squared. Okay, for a given speed, the radial acceleration is large when the radius of curvature is small. So in other words, if the radius of curvature is small, the acceleration is very, very great because it has to turn around very quickly. For the radial acceleration is small when r is large. In other words, if it's the curvature is very large, the acceleration isn't that great. You imagine going around a very slow curve. You don't feel what we're going to call the centripetal force as much as if you turn around a curve real fast and a tight curve. You feel it much tighter. So the radial acceleration is large when the radius of curvature is small, and the radius of the radial acceleration is small when the radius is large. Almost sounds counterintuitive, but that's the way it is. The direction of the tangential acceleration is either in the same direction as v, the v is increasing, or opposite v if v is decreasing. I already pointed it out, but look at point B. You can see that the tangential acceleration is pointing backwards to the assumed velocity, which just means that it's slowing down. It doesn't mean that the velocity is going in that direction. It just means that the velocity is slowing down as it goes up the hill. Okay, now for uniform circular motion, v is constant, tangential acceleration is 0, and the acceleration is always completely radial. Uniform circular motion is a special case of the motion along a general curved path. If the direction of the velocity does not change, there is no radial acceleration. So motion in one dimension, was in a straight line. In that case, the radial acceleration is zero, but the tangential acceleration may not be 0. It could be slowing up or speeding up or slowing down. Okay, let's do some quizzes. A particle moves along a path and its speed increases with time. In which of the following cases are its acceleration and velocity vectors parallel? Okay, a particle moves along a path and its speed increases with time. In which of the following cases are its acceleration and velocity vectors parallel? When it's in a circular path, when the path is straight, when the path is a parabola, or never? What do you think? Well, it has to be straight. In other words, if the acceleration is parallel to the velocity, there's no direction component to the acceleration. It has to be in a straight line path. Okay, now a particle moves along a path and its speed increases with time. In which case are its acceleration and velocity vectors perpendicular everywhere along the path? When the path is circular, when the path is straight, when the path is a parabola, or never? Think about it. Oh, well, you might think, well, if you have centripetal acceleration, it's always perpendicular to the velocity. But notice the question. Read the question. A particle moves along a path and its speed increases with time. The fact that the speed increases invalidates A there. Because if it's increasing, it's not circular uniform motion. So the answer is never. The answer is never in that case. If the acceleration vector is to be perpendicular to the velocity vector, it must have no component tangent to the path. There go the dogs again. Sorry about that. On the other hand, if the speed is changing, there must be a component of the acceleration tangent to the path. Therefore, the velocity and acceleration vectors are never perpendicular in this situation. They can only be perpendicular if there's no change in speed. Now let's do an example problem. A car leaves a stop sign and exhibits a constant acceleration of 0.3 meters per second squared, parallel to the roadway. The car passes over a rise in the roadway such that at the top of the rise, it's shaped like an arc of a circle of radius 500 meters. At the moment the car is at the top of the rise, its velocity vector is horizontal and has a magnitude of 6 meters per second. What are the magnitude and direction of the total acceleration vector for the car at this instant? Okay, let's conceptualize this situation using the figure and any experience you have had in driving over rises in a roadway. I know there's sometimes you get that almost that if you're going fast enough and the bump has a radius enough, you almost get that roller coaster feeling of being weightless for a moment. But those are rare occasions. Because the accelerating car is moving along a curved path, we categorize this problem as one involving a particle experiencing both tangential and radial acceleration. We recognize that it is a relatively simple substitution problem. The tangential acceleration vector has a magnitude of 0.3 meters per second squared, as stated in the problem, and is horizontal. The radial acceleration is given by minus v squared r, with v equal to 6 meters per second and r equal to 500 meters. The radial acceleration vector is directed straight downward. Okay, now let's evaluate the radial acceleration. Find the magnitude of a. Well, a is equal to minus v squared r, so it's, oops, I jumped the gun. Minus 6 squared over 500. So that's 36 meters per second squared divided by meters. You're going to get meters squared over second squared. There's an error there. I see an error there. That should be minus 0.0720. It should be meters per second squared. Remember, this is an acceleration, so it has to be meters per second squared. They just misprinted it on the slide. Okay. Oops. For the angle, use a sketch of the vectors. Oops. Let's see. I missed a. Evaluate the radial. Find the magnitude of a. Oh, all I gave you was the radial acceleration. That's the minus 0.072 meters per second. Now let's find the magnitude of a. It's the square root of the radial acceleration squared and plus the tangential acceleration squared. Well, we get the minus 0. And they even have it. They have it right here, 0.0720 meters per second squared. You square that, and you add that to the given tangential acceleration, which is 0.3 meters per second squared. And if you put that into your calculator, you'll get an acceleration of 0.309 meters per second squared. Now, to get the angle, let's draw a little. You see the phi. You get the tangential velocity going this way, and the radial velocity going this way. So the total acceleration, or to get the angle, you get a equals the tangent inverse of the radial acceleration, which is minus 0.0720 meters per second squared, divided by the tangential, which is 0.3 meters per second squared. And if you work that out, you get it's minus 13.5 degrees. And you can see that it's pointed below the x-axis. Okay, this ends our discussion of tangential and radial acceleration. The next section will be 4.6, relative velocity and relative acceleration. All right.